Hello everyone and welcome to the Geoscience Training, the third session, I should say, of the Geoscience Training for the C-STEM Challenge. And as you should know by now, but if you haven't been introduced to me, my name is Roy Carter, and I currently work for Chevron in the strategic planning, but I have a background in engineering, actually chemical engineering to be specific. And so right now, what we're going to do, we're right in the middle of our C-STEM Geoscience Challenge. And so what we're going to talk about today is a lot around where you should be in the entire process around developing a solution and developing a prototype to solve that solution. So with that said, let's go ahead and jump into it. Okay, so the first thing is, this is a pacing guide that everybody should be familiar with. And so right now, as you can see at the January 10th, we're in this fourth cycle. And so right now, hopefully you and your students should be working to design a prototype. And so the prototype for the C-STEM Challenge. And so that's where we are. So the previous cycles, they were around how to do your research, what exactly is the C-STEM Challenge, how to do your research, and also how to go about collecting your resources. And so if you have any additional questions or need to refresh, please feel free to go back and take a look at any of the PowerPoint presentations that we did. They're available to you in the C-STEM Break library. And I highly recommend, if you have any questions around what exactly is a pipeline, what is some of the research that I recommended that you do, and also some resources that are available to you, please feel free to go refresh your memory before you jump into designing a prototype. Now, with that said, as you can see, January 10th, the actual C-STEM Challenge is going to be coming up very soon. So I highly recommend that if you haven't really started on the entire Geoscience Challenge, I would recommend that you go ahead and start. Don't hesitate. There could be a lot of work, and it's a very interesting problem. So let's jump into the problem. So the Geoscience Challenge is about, what is it about? It's about pipelines, as I said before. And so the overview, so I'll just read the overview to you. So it's all about building new pipelines and updating existing ones. And then one of the things that the American Society of Civil Engineers does, and it's an American company it's a nonprofit representation of all the civil engineers. It's basically a trade industry group. And so they release a report card every year on the condition of infrastructure. And then one of the things that they found is that the oil pipeline infrastructure is in poor to fair condition, and it's mostly below standard. And then also a large portion of that system exhibits significant deterioration. And so condition and capacity are of significant concern with strong risk of failure. So one of the things that, if you did not listen to the previous PowerPoints, or previous teacher trainings, I should say, is that we went into depth about how a pipeline works, what are some of the problems facing pipelines, and also we went into some pipeline problems, not pipeline accidents that happened in the past. And it's very interesting. So feel free to go back, as I said before, and review some of those previous presentations. We're not going to dwell on them here. Well, I'm assuming that everybody is right up to the point where they followed along and now they're ready to build a prototype. And so also for another thing that I want to emphasize within this Geoscience Challenge is that you and your students will be creating a functional geoscience model that demonstrates how improvements to the energy infrastructure will make it more reliable and sustainable in your region to improve your grade on the ASCE report card. So don't let this intimidate you. Basically, what we're looking for is a solution, some type of solution to some type of problem that you've highlighted in your research. There's a number of problems facing the current pipeline infrastructure. And so what I would highly recommend is that your students pick one of the many different challenges facing the pipeline infrastructure currently in the United States, and then focus on that and try to think of some improvements of how you can actually go about solving that problem. And then also, just to emphasize, also what we will be looking for at the C-STEM Challenge, at the Geoscience Challenge, we'll be looking at all geoscience project submissions they have to be accompanied by some type of scaled engineering design, along with a drawing on 8.5 by 11 graph paper. Okay, and so also we are recommending that the groups use Prezi to present, and then so this is going to help when you go in front of the judge, or when students, I should say, go in front of the judges, is that it's going to be able to share, because we're going to ask them to present their improvements to the judges. Okay, and so also one of the other thing that we're asking is that the geoscience model not exceed 3 feet by 3 feet by 3 feet, and that the oral presentation that I talked about should be presented by 2 team members and then not exceed 5 minutes. Okay, so one of the things that in the previous December 6th session, session 2, one of the things that I gave everybody was some homework. And one of the things that I emphasized is actually just to go take a look at the ASCE infrastructure report. It's actually very interesting. That the overall report, the ASCE came out and said the United States infrastructure overall is in very poor condition. They actually gave it a D+. And I believe the pipeline section got like around a C, C minus, somewhere around there. And also another thing that we discussed in the last session was we reviewed historical pipeline failure incidents. And one of the things that your students should come away from this discussion about is really to understand how critical the pipeline infrastructure is to the U.S. economy. And then also, well, once you get into understanding pipelines, one of the things you'll find is that a lot of pipelines that we are dependent on right now are made out of iron, usually cast iron or wrought iron. Now, I went into what are the differences between cast iron and wrought iron in the previous teacher training, and then but also they're typically very old pipelines, and they have a number of different mechanisms of failure. And so also another thing that would be helpful to understand, because all this understanding, and the reason I'm talking about this now is that it's going to help you to understand the problems that are currently facing pipelines and also help to develop solutions. And so one of the big problems with cast iron pipelines is corrosion due to pitting. And this is a very common mechanism of failure. So if you can deal with there's a number of different solutions to how to eliminate pitting. So this could be also another avenue of investigation for you and your students. So now what we are asking all of the team to do is actually how to create a solution. So my job here is not necessarily to tell you what to do. It's really to kind of give you a coach. You're kind of like to coach you and give you some guidance in terms of like what type of solution should you do. So first off, the first rule is there isn't a correct answer. There are a number of different things you can investigate. So what I would emphasize to each and every one of you listening to me today is first off, be bold, be creative, and don't be afraid to try something new. And so there's a number of different steps you can take to create a solution. So first off, the easiest way I would say to go about this solution is first off, think about where you live. Okay, I'm currently right now, let me just step through this coming from my perspective. I live in Houston. So what is Houston known for? Oil and gas. So therefore we have a number of different types of oil and gas pipelines because we have a number of refineries that are located to the east of Houston. Actually, Houston is one of the major petrochemical areas within the United States. So the pressing pipeline issues where I live currently in Houston are all centered around oil and natural gas. So therefore, if you look at number 3, which system do you want to investigate, it would be pretty sensible for me to try to hone in on oil and natural gas. But if let's say you live in another area of the United States, there's a number of different pipelines in terms of water, sewage, that's just also gasoline. There's there's pipelines that pipe a number of different substances. You don't necessarily have to study oil and natural gas pipelines. There's also issues around water pipelines, drinking water, and also sewage, so dirty water coming out. And so once you do that, try to get an understanding of how your current system works within the area that you want to investigate. Like, so when I say that, I would like map your chosen system. So let's say you wanted to do water in the Atlanta area. I would contact, let's say, the water department, and I would try to get an understanding of where are the main water mains that are currently located in the Atlanta area. And then I would say, I would add, maybe just ask them, how old are they? What are the current issues that you are facing in the system? Are there any bottlenecks? This goes to number 5. Are there any bottlenecks in the current system? And then what are any kind of solutions that you have developed in order to help go through these bottlenecks? Now, one of the things that I would recommend is that the system is that this would require you to at least go out and talk to a couple of engineers or people who are responsible for these pipelines, and they would actually you'll be surprised to see that a lot of people would love to talk to you about this about these type of topics. So don't be shy. Don't be hesitant to go out and reach out and talk to people in the community about these situations. You actually learn a lot. It's very interesting once you dig into it. Now, with that said, let me just jump into a couple of potential solutions. Now, these are just potential solutions. Don't necessarily think that you have to do these. This is just some things that came off the top of my head that I would want to investigate, but feel free to, this is just from how I'm thinking about the problem, but feel free, if you're thinking about the problem in a different way, to go about your solution in the way you see fit. So now with that said, one potential solution is pigging. So you hear a lot about pigs within pipelines. Now what they do, in order to clean out a pipeline, they put these devices within the pipeline called pigs. So therefore, think about how would you clean out the inside of the pipeline. So as you see from the bottom left-hand picture, this is a utility pig. And so they put this pig, this device inside the pipeline, and basically it pushes down the pipeline, and it basically scrapes off any debris that are located around the sides of the pipeline. Okay, so that's a utility pig. And also you have things called inline inspection pigs. And so those, what they do is they use like scanning technology to try to understand what is the condition of the pipeline, try to identify any corrosion problems. And so one of the things you can think about doing is how would you potentially incorporate pigs into your solution if that's an avenue that you want to go down. And as you see, they can be significant. They can be very big devices. Because if you look down to the right-hand side of that right-hand picture, there, I mean, the pig that you see there is literally as big as a person, bigger than a person actually. Because you think about some of the pipelines that we have for transporting huge amounts of volume, and so they have to be big pipelines. And so you need a pig as big as that to go through that pipeline. Now, another potential solution is remote surveillance. So think about pipelines. The reason pipelines are so valuable is that they're able to basically link up sections that are like separated by a wide distance. So therefore, they're going across a large amount of basically unpopulated area. And so one of the questions that they have is how do you do remote surveillance? But typically what you would have to do is have people basically drive along the pipeline pretty much on a very regular basis to check the pipeline and check the condition of the pipeline, make sure that there's no leaks coming out the pipeline. But one of the things with the whole drone technology that's come up is that they've realized that, hey, we can do surveillance of the entire pipeline very easily using these drones, because therefore the drone allows access to remote areas. You can store these images, and then as you store these images, you can also compare them against future runs, so you can understand. Let's say you do have a leak that develops in a pipeline. You can go back in the past and see when did that actually develop, which is actually very important. And also, another thing that people have found is that animals behave around pipelines a lot differently than they behave in the forest. And there's a number of reasons that we won't go into, but one of them is pipelines tend to be a source of heat. And so animals tend to congregate around pipelines. And so how can you monitor that behavior? Because if you drive up in a truck, animals are going to disperse. And so what they found is that drones actually allow you to monitor animal behavior near the pipeline without disrupting animals. So this is another solution. Feel free to take this solution and use it or not use it if you see fit. But just think about how if you had owned the pipeline, how can drones be incorporated in helping you do remote surveillance of the pipeline? So right now we're at 15 minutes, so therefore I don't want to go on any further. But one thing that I would highly recommend to everybody is just go ahead and start. If you haven't started, feel free to start. If you need any help or have any questions, feel free to contact me. As you see, my contact information is at the top, Rory Carter at Chevron.com. And therefore, I'll stay on until I believe we might have by roughly 10 minutes or so left in this session. So if you want to chat with me live right now, I'll hang around for about another 10 minutes. Therefore, if not, feel free to contact me at any time. And I'm looking forward to working with all of you and looking forward to seeing what your solutions are. And I will see you next month at Workshop 4. Okay, thank you very much and have a good day. Bye-bye.
Hello and welcome to Everyone is an Artist and Engineer 2014-2015 Energy Infrastructure, Wind, Oil, and Natural Gas VEX Robotics Teacher Training for Elementary. Today is January 10, 2015. I am your instructor, Felipe Resendes. If this is your first time, welcome. But we will encourage you to view some of the previous past videos so you can understand a little bit more what's going on so far in the training. This is part two of a how to build the ClawBot for VEX Robotics. Academic Year Pacing Guide. Today, Saturday's workshop. We are currently on cycle 4 under the design prototype for the interdisciplinary connection. Students will design their prototypes of their C-STEM challenge project solution. At this point, if you haven't done so, we would encourage you to build at least to part 1 so you can have a good understanding of what's actually happening from now on, and will be part of the engineering design phase that we're going to see on the next screen. Right now, we're currently looking at Create, which makes a prototype and test it. Again, if you're now starting, I would encourage you to pretty much take a proactive approach at this point, since we are actually looking into about 90 days before a competition, and there's a lot of work that still needs to be done. Training outline is going to be a very simple one today, not very extensive. We're going to basically go over building the ClawBot part 2, which we're going to give a quick part. We're going to continue with the parts, and then we're going to be actually focusing on parts 16 to 27. And then I'm going to provide some really good hints and tips for those of you that are here with me today and have endured waking up on a Saturday. So hopefully give you the advantage in competition. We basically left off last time on section 16 here. And on section 16, we're looking at the base of the actual robot that we're working on. We're looking at basically installing this motor here with this collar and this shaft, and we're starting to add the sprockets that eventually will turn the actual wheels on your robot. And we're looking at 3 sprockets, one in the center of the motor and one on each wheel. That's going to be sandwiched in between the collars and tightly squeezed before you put the shaft. As you can read here, push collars tight before tightening set screws. Is very important that you actually do this, or your wheels and your basically your sprockets will not be making contact, and they might be skipping or they might even become loose. So make sure that we're actually following it correctly. We're looking at the bottom again. You are going to need a couple of collars and fully insert the shaft into the motor. So now that you've installed the motor in the previous pass, we're going to actually insert the shaft straight through. And on 16, we're seeing it here. And then we're seeing it here at the very top. Push collars together before tightening set screws. Again, make sure everything is really tight in between the actual motor and the frame. On 17, like I mentioned again, we're pushing the collars together before tightening the screws. And now you're seeing that you're going to need 2 shafts, multiple collars to go into the setup that we did on 15, 14, and 13. And again, we're going to push the collars together before tightening sets of screws. So basically, you're pushing everything in really tight and then adjusting this collar so it doesn't move anymore once it's in. It doesn't let it go out of the other side. On number 18, basically, you're doing the center sprocket right here. What's going to actually be the rotational with this motor will be rotating and lifting up the arm. And again, you have, you have some screws. These are actual screws, and you're going to have a spacer in between the ST1 and your 2 sprockets. For 19 to 21, we're going to be basically focusing on the actual arm. On number 19, you're looking at where the actual sprocket's going to be placed. As you can see, the faded background here is going to be running through the actual sprocket. I mean the actual beam here. The C clamps beam. It's going to go right in the middle, and then you're going to fasten it with some other screws, the S4, and then some nuts to actually keep it in place. So remember, this will be the end case for these to keep it in place. So now we're attaching it, as you can see right here in this picture. You're screwing it to the actual shaft on this side, and then we're adding, we're going to continue adding. Number 20 basically is just adding the actual claw, nothing more, but then actually just bringing the claw out and actually securing it to the same beam on 19. So now we're actually extending the arm and actually producing the pickup mechanism in this case. You're going to need some S12s, 2 of these, and then you're going to need some LOL, 2 of these NLs. And again, if you don't remember this, go to the very top of part 1 of building the claw bot, and you'll be able to pull out all these little parts and how they look like a little bit better. Again, when it's done, this is how the claw should look like. On number 21, we're focusing on the actual shaft that's going to go, how the collar looks like, so it can give you a better idea how the actual spinning axle is going to be and how it's going to support. Because remember, you have a motor here that's turning, and then you have also another collar and motor that's going to assist with this particular process. So you have 2 sprockets that are going to be moved by this little collar here at the bottom. So this collar is going to be inserted right where the motor is at, right below it. So as you can see, it's going to flush down, and then you're going to add a shaft and a collar to keep it in place. So now it's running right through the middle, right through here, and it's going to be placed near the motor. Fully insert shaft into motor before tightening shaft collar. So it's going to go right through it, and that's going to be the motor that's going to be turning the actual sprockets here. So this is an actual shaft metal that goes right through it. And this is the front of the robot, so you can get a better idea. On number 22 and 23, we're actually looking at inserting basically squeezing together before tightening collars. So make sure that you squeeze these beams because they might be a little bit not tightening properly at the base. Make sure you squeeze them together, and when you actually put the actual collars and the shaft across, because it'll help push out and keep the arm from moving or wiggling out a little bit better. But that's basically it. Chapter 21 is actually landing and setting the actual arm. Again, for a robot, check that the arm rotates up and down smoothly with minor motor resistance. You should be able to move it up and down, and the arm should actually, you should hear the motor as it turns and spins with the shaft collar and the actual sprockets up here. 23, we're now looking at number 23. Basically, at this particular point, is adding the actual battery strap. The battery strap is very important because that's what's going to keep the battery and your power in place, and you don't want that thing floating around or falling during competition. So make sure you're actually securing these little straps together with 2 of these BSTs here. Looking in the top here, you're going to need 4 actual little short screws and actual the little nuts on top. And it's very simple. Just put it through the beam where it's located here, and again, mount battery strap under the chassis. So it's going to go underneath right here where we're actually pointing out, actually somewhere around there. It's not quite right there. Again, continuing with number 24 and 25, guys, is actually this particular step is the step where we actually insert the actual Cortex. So be very careful with this one. The Cortex is going to have some holes on the edge. Don't over tighten them. Make sure that when you put the bolts and the nuts, go ahead and not over tighten, because this might actually break. It is made of plastic, and as you can see here, they will break if they over tighten them. So be real careful with it, but you want to have it secure. You don't want it loose and coming out of competition, because as this starts moving, your motors are going to start, your connections are going to start moving off, and your robot might stop working. So keep that in mind. Right here, we're going to need 4 screws, and we got the VEX next, and it's going to sit right on top right there. So it's going to be between this frame and this frame right here, right on top. Is a better picture over here. Number 25, we're almost at the end here, guys, of building the actual claw. There's nothing much that we're doing here, but other than adding a support beam from the front to the actual tower where your arm is. There's a lot of force happening, especially rotational force. When the motor's being running and the claw's going, it could go really fast. So we need a little bit of counter balance here, and this is what these little steel beams are doing. So you're going to need 4 screws, 4 nuts, and we're going to attach these little beams, which on the next segment you're going to see what's happening. So we're going to basically do what's happening here. We're going to actually we're building them, attaching them to the front, and they're going to go across and up and we're going to attach them to the actual beam. And again, it tells you how to do it here. Once you set it up, we're going to do it. We're going to bend it towards the actual sprocket, and then we're going to bend it on top again. So basically, kind of like a crowbar of some sort, a little lever. So once you do that again, attach it to the top and to the bottom, and with 4 short screws, 4 nuts, and then this will be your front end robot. Your robot should look something like this when it's all said and done. And this is basically the last couple of steps here for the actual robot. So there's really not less to do at this point other than going out there and actually getting it done. A couple of hints and tips, guys. It is very important that you pay close attention. I know I mentioned it here before, but I just wanted to illustrate it now today. For those of you that never worked with robotics, this is the way you're actually gonna connect the motors. The motors are gonna come with a black wire and a red wire. You're gonna plug in the red wire towards the center of the controller, okay? But every motor, it's gonna basically go into with a motor controller. You need to have these there, or you run the risk of burning a $30 to $40 motor instead of a $9 or $6 little motor controller. The motor controller is kind of like a resistor. It helps you out, and it doesn't allow your motors to go bad. Okay, it's the first line of defense. So when you're doing this, go ahead and do that. But make sure that you also connect the motor controller correctly, because if you put it backwards now, you're going to have some problems. Make sure you connect black to black and red to red, and we're showing it right here. On the next option that we have here, we're seeing a more Porter 6. So this will be with the actual different motors, with the actual controller. The controller has some default code, like I mentioned before, and this is just telling you the motor port numbers are going to go. You're going to see on the picture here in a little bit that it's going to help you. That's going to help in just a bit. And right here, the ones that you're adding a motor controller, we're looking at the claw motor and the arm motor, because those are going to take a lot of force, and they might overheat the motor much faster than the actual left drive motor and the right drive motor. There's you want to do that because you want to add the motor controller, because, like I said, it can burn out your motor, and it's hard to replace a motor. It's easy to replace a motor controller. In this case, we are putting them in the actual claw and arm. But if you have some extra motor controllers, go ahead and put them on all. Strongly recommend it. The default code is going to make you arm up and down right here if you press the button. The claw is going to open and close if you press the top left button, and this is the way it's going to drive: forward, backwards, forward, backwards. It's kind of like a tank drive. So if you turn one stick forward and one wheel back, it's going to start rotating in one direction. If you do it the opposite, it's going to do it in the opposite direction. Both sticks going forward is going to go forward. Both backs should go back. Right here, we are actually looking at the claw motor, arm motor, left drive motor, and right drive motor. And here's a blow up of what I was talking about. Your left drive motor is going to go on port 1. Your right motor is going to go on port 10. And your claw motor, which is going to be with the motor controller with a 3-pin, should go into the port 6 and port 7. Now, if you add a motor controller to your motor, you must pay attention to this, because now you're going to have to change your port number to port 2 and port 9 if you do add that, and you're going to have to change that in your programming, which we'll cover next couple of sessions. And again, this configuration is based on a Cortex microcontroller default code. This is the default code that comes with the actual motor. So pay close attention. Very important, very easy to do. If you follow this, there's no reason why your robot should be working from right out of the box. Another hidden tip. Now, for those of you that are speed fanatics and speed freaks, or need to take an edge, this is something that I wanted to tell you. You can change a high speed to a low torque motor, optional configuration. So basically, you can change the high speed mode into high speed mode, which provides 60% faster rotational speed with a 60% reduction in torque. So you're not going to have a lot of torque, maybe to move stuff right away or carry a lot of heavy objects if you're going to be carrying, But the motor should be strong enough to move, But if you do this setup, you're going to be able to run a lot faster. You're going to see that your motor's going to, your robot's going to really move. How do you do it? We follow these simple 8 steps. Number 1, we remove the 4 screws on the top of the corners in front of the motor case. So you're removing 4 motors. They're 2 and 2 long. They're very special. Do not mix them up. Don't throw them with the other POW, because these have to go back in the same place. Lift the top of the cover. Do not disturb the gears inside. So basically, we're just removing the cover. Don't be afraid. Remove the black cover. It might be a little bit tight, so go ahead and use a little bit of force. Number 3, lift off the output bushing and place to the side. This will be used later. Now, and this bushing is this one right here that you're looking at right there. It's going to be a little bushing on top of kind of like a shaft here. Moving right along, number 4, move the middle gear and the output shaft gear. So you're going to move these 2 gears, and now every new motor that you got, it's going to come in with some special gears. Now they're typically separated. Now I hope you took very special precaution and instead of just throwing them around, these are the gears that when you open your motor box that are in there, that's what they're going to be used for. And you're going to switch them out. You're going to see a change in teeth on the gears and the amount of gears these teeth have. So install this the high-speed middle gear, and install the high-speed output shaft gear. So you're going to replace these 2 with the 2 that were in the box. And basically, number 7 is that simple. Install the output bushing removed in step 3. So now this bushing that you removed up here is going to go back in its place. So you're only replacing 2 of the gears, and you're putting everything back together. Make sure the bushing orientation is as shown. So make sure it's correct. It's pointing where it's at, to this direction. Finally, replace the cover and the 4 screws, removing steps 1 and 2. So you're going to lock it up and ready to go. If this works successfully, you should be able to have a very fast robot. You should be able to see a significant increase in speed, and maybe give you that extra advantage during competition. So go ahead and pat yourself in the back for being here with me today. This is basically some little extra hints that I threw out for you guys for coming out today. Again, our next session is going to be February 7th, 2015. I will go over, hopefully, with the installation of the actual program, Robot C, and explain Robot C a little bit in depth, with the effect of hopefully getting you guys familiarized with the software. The sooner you do it, guys, the better. There's a lot of documentation on the web. If you want to jump the gun and get ahead of me, it's always best to already have your feet wet if you're new to robotics, especially VEX. The software, I think there's a new version out, 4.x. So it is actually new for me. I've seen a lot of new stuff, so I will be learning along these next couple of days and hopefully be able to give you guys some advice. But they also have a text-based on the background that we can use, like the older versions of VEX per Robot C. Again, also coming up in the near future, I'm going to hopefully give you guys an outline on what to expect for competition day, maybe some tips and hints that you guys want to prepare for in our next session as well, because next session of installing the software shouldn't take us very long, but at least it'll give you a good platform on what to do in case you will fall in trouble. Again, thank you, and see you next session. And I apologize, it says here next year's session, but this is from December, and it's next session February 7th, 2015. Thank you. Welcome to Everyone is an Artist and Engineer 2014-2015 Energy Infrastructure Wind, Oil, and Natural Gas VEX Robotics Teacher Training for middle school and high school. I'm your instructor, Felipe Resendez. Under the Academic Year Pacing Guide Saturday Workshop, we are under Cycle 3, January 10, 2015, under Design Prototype for Interdisciplinary Connections. Basically, that means that you should have your students already at the point where they will design their prototype or prototypes of their system challenge and projection solution. So if you haven't already gone through the first couple of phases of the engineering process, you should be at the construction phase at this point, just to kind of give you guys a quick overview. Today's training outline, we're going to go over programming. What is programming? The top 10 programming languages currently in the market or in the industry. We're going to go over sample code in Robot C. Just a brief on the sample code, what it might look like. No real coding today. Hopefully in the next sessions coming up, we'll be able to actually go over some code and run it and compile it and show you how it actually gets loaded to the actual robot. We're going to be installing Robot C, which what requirements are needed for a new installation. The license manager, if you already pre-installed, if you have already pre-installed the software, you have it installed as a trial basis. And we're also going to go over the installation process, and at the end, a couple of hints and tips. What is Robot C, or what is programming? Programming is a process of creating a sequence of instructions that tell a computational device, and this could be a computer, or in this case, such as a microcontroller on a VEX robot, how to perform a task. The VEX ARM Cortex-based microcontrollers are pre-programmed with default code that allows you a simple way to get started without writing and downloading code. However, more complex robot configuration and behaviors are possible through programming. So again, there's default code that comes automatically with your controller that gets built into it already from the makers of VEX. There are several options for creating and downloading programs to your VEX robot, such as Robot C for VEX Robotics. Another option might be ACC as an alternative if you feel more comfortable using ECC, or something you guys might be able to use as well. Using Robot C graphical mode, you can drag and drop blocks of code from the graphical functions menu to create a program even faster. Robot C has switched to a graphical mode almost as the other GUIs like LabVIEW and etc. that are currently very popular in the market. You'll see this version as the version 4.27, if my memory serves me correct, on this particular installation later on. There are two types of code with Robot C. We have autonomous code and radio control code. Autonomous code, what the name implies, autonomy means that by itself. Autonomous code allows a robot to perform behaviors without input from the radio control transmitter. The robot follows pre-programmed routines responding only to sensor input. So basically, this is basically the robot doing its thing. Kind of like cars nowadays are starting to drive by themselves. I mean, they have all these sensors that have been programmed to do specific functions. Once they hit those parameters or behaviors or limits, they'd be able to do the programming that's been added to them. And without any user interaction, because you do have eventually control of the robot, kind of like a wireless RC card towards the towards the competition. Now, radio control is the one I was talking about a second ago. Radio control code allows you to configure the way in which the radio control transmitter controls the robot, allowing a human operator to provide input to the robot. So if you select to open a claw on the X button, it will open the claw. Or if you want to do it as a up and down stick, you can do it as well. But that's you actually allowing and configuring the actual radio control transmitter. Those are the two types of robot codes, and there's a mix: autonomous code and radio control code. Some competitions like FRC allow you to do that, or I'm sorry, First Tech Challenge allow you to do that. First couple of seconds are autonomous code, and then it switches over to radio control code. Best Robotics allows you to do the same thing as well. Top 10 programming languages. Now you may ask yourself or your students, why do you want to learn programming? Where here are a top 10 and what some of the applications that are currently being used at. Um, According to the results, here are the top 10 programming languages of all platforms: mobile, web, desktop, and embedded. Uh, Anything you use from your VCR has to be programmed. There's a firmware that gets installed, so it recognizes inputs. Your mobile devices, the World Wide Web. This right here is the actual World Wide Web. Then we have mobiles right here and computers. So Java is almost on these top three and very popular, followed by C, which is a version of Robot C. C and C++ are pretty much brothers and sisters. They are in the same area in how you code. So on all these, you can have them on their phones, computers, and actual circuitry for different types of electronics. So as you can see, C is pretty high up there. We have Python, another very popular programming language, PHP for programming web servers and database servers. JavaScript, again, a version of very similar to Java, it just allows to add functionality to the actual websites and stuff like that. Ruby, which I've never worked with, and R, and I have worked with a little bit of MATLAB. So those are the top 10 programming languages in the IEEE spectrum, and they come up with their own criteria on how they came up with these top 10. What you're looking at right now on your screen is a sample code in GUI interface. This is Robot C. At least in the last couple of years, this is what the code would look like when you were writing your code. Task main would automatically be put there by the actual, if you wanted to do a motor or a movement, you actually do under motors moving forward, and it would automatically input all the tasks here. So there's not a lot of coding except for what you're going to do on the parameters. // go forward at full speed. Again, when you see / here under hint, Robot C will allow you to document your code in green text by adding two /. This here, you can add as much code as you want. And we recommend you guys that when you're writing code line by line, what is happening? What are you doing? I would even code every line, like example, code line 4, motor left going 127 or full speed. You can actually code as you go along off to the side as well. And line by line, motor, run motor forward and then stop for 1 second. So while moving forward, compile on, and it was compiled. This gives you the date that it was compiled. Which basically is when it's actually processed, so it can run the actual code. Compile. If it doesn't pass the compiling and there's errors, it will not be able to load to your robot, or it's going to have errors, and your robot's not going to do what you think it's going to do. So it's very important that there are no errors when you compile and load and send it to your VEX Next Cortex. But this is just the very basic. As you can see, a lot of your simple command windows are up here, and these are very similar to you. You've been using it for many years, and of course, this is your function library that you use to actually call up all the main servo, sound, timing, motors, etc. Hardware requirements for a new installation. While setting up VEX, you need Windows XP Service Pack 2 or later. I just strongly recommend you guys face off XP because it's no longer being supported by Microsoft. So be real careful. Go ahead and at least try to have Windows 7 as a very comparable operating system that I feel very comfortable with in the last couple of years, and even Windows 8. Hardware needed, VEX programming hardware, AA cable. That's the USB cable, the long one that has 2 identical sides, and then your orange programming cable, and an orange programming cable. 2 VEXNet USB adapters, a VEXNet Cortex, and a joystick. So you're going to need all this. Other considerations, make sure that you're actually a local computer administrator. You'll be able to install software. If you're not, I strongly recommend you go to your IT department and the person in charge of your school and see if they can get permission to install the actual Robot C. If you already installed Robot C 4.0 manages your Robot C and Robot Virtual World licenses. It is designed to simplify the process of keeping all of your software up to date while minimizing the number of downloads and installations you must perform. Once you have downloaded any version of Robot C 4.0, you have everything you need. NXT and Cortex drivers excluded. So if you're working with NXT or you need to download the drivers. No additional downloads of Robot C software are required. In fact, don't try to download and install additional versions. So if you already have one version, don't re-download a 4.1 or a 4.2 or 4.7 if you already downloaded 4.1. And you can always get more information on the resource link mentioned here down here. Installation process, go to the www.robotc.net/download/VEX and select on the Robot C version 4. So you're going to go to the downloads pull down menu and select the VEX Robot 4. You can even, there's also, I believe, if you're more familiar with Robot C 3.x for Cortex and PIC, you can also, I would stay away out of these, but I'm sorry, for VEX. It might work, but you just want to make sure you select VEX Robotics. Click on the blue download button, version 4.2.7 when you see this, once it comes up, and save the program to your computer and run installation. I encourage you maybe to the downloads or to your actual desktop, so somewhere you can know you're going to be able to have easy access. During the installation process, you're going to see a couple of screens. The welcome screen, go ahead and just click next. This is the EULA, or the user license agreement. Make sure that you select accept the terms and license agreement. If you're like me, I like to read through this stuff. I don't know why, just one of those crazy things I like doing. 99.99% of the people don't read, but I do like to read some of the stuff. I want to say more than 80% of the time. Installation process, click finish and complete installation. So once you go through it, it's gonna ask you to come up with this particular setup. Click finish. Okay, and if you already if you were issued a license from the system staff, I'm not 100% sure this is going to happen to everybody or who's requesting a license, but you can actually go to manage license. You can click add license button, which will be right here at the bottom, and then we can go ahead and add your license ID and password, so you can have the latest version for the allotted amount of time the license has been purchased for. And a couple of hints and tips, which I won't take any more of your time, is do not forget to install the USB driver. So you're having issues that it's still not connecting or not reading your computer. It's definitely the time where you can go back to the Robot C web page, which is here, and go ahead and install some of the firmware or updaters before using Robot C. Make sure if right here, recommended downloads, USB to serial drivers, etc. that you might need for this particular process. Again, thank you, and see you on the next session for February 7, 2015.
Hello, everyone, and thank you for joining me for the third Saturday workshop here on January 10, 2015, our first Saturday workshop of the new year. For those of you who don't know, my name is Orlando Benitez. I'm the graphic and web designer at CSTEM. I built a 3D printer and actually installed the software myself at the office. So, as you can see here, we're in cycle 4, January 10th, and we're in the design of prototype stage. That means at this point you should already be familiar with how to use or how to get the software Google SketchUp, which is the software that we'll be using, and how to start manipulating basic features of it. So today we're gonna cover some more in-depth or some more techniques on how to use Google SketchUp more efficiently. That way you can start designing your prototype today, or soon actually, I should say. So first we should start by talking about minimum feature size. So what is minimum feature size? So essentially what minimum feature size means is essentially the smallest dimension that a 3D printer can print without making the model unprintable. So what does that mean? That means that the minimum feature size is the minimum size that your printer can print. If you think about it, 3D printers have filament that or a material that gets fed in through a pipe, and the material is only so thick. It's only so thin. So when it gets melted and it gets printed through a little nozzle, it can only be so small or so thin, because or otherwise it won't print it at all. So that's essentially what minimum feature size means. So the minimum feature size is often set by the thickness of the layers that can be created by a 3D printer to make the object. So it's typically between 0.1 and 0.4 millimeters, which is really small, but there is some models sometimes where they get really sharp edges, or there's some models that have like really small corners, and the printers, depending on your printer, some can print really thin and some can print thinner, but depending on your printer, or most printers won't print super thin edges. So that gives you a good idea of how thin your model should be in certain areas. So this is 3D. Another thing that 3D printers can print is unsupported overhangs. Think of an overhang kind of like on a cliff. Since 3D printers create objects by building layer upon layer, it becomes difficult for the layer to remain in place if it's part of a layer that hangs out past the end of a previous layer too far. So think of Legos when you're stacking layers of Legos, but you're starting to hang Legos on the one Lego part where they clip. I don't know if that makes sense, but some Lego blocks have 4 points where you can clip Legos too. But if you start getting overhangs, at one point your overhangs are going to start falling apart because they have nothing supporting them underneath, kind of like a bridge. I guess that would make more sense. A bridge, if it starts overhanging too much, you're going to want to put some supports underneath it to keep it to just keep those overhangs from falling down. Hence the name unsupported overhangs. So here's an example here. A common rule of thumb for unsupported overhangs is that if the angle in which the overhang is at is more than 45 degrees, then for the most part you're gonna want to need some supports underneath that. And that's because 45 degrees is usually kind of the printers can handle 45 degrees. But if it's any flatter than that, if it's small, if the degrees, if you can see in the picture here, if it's smaller than that, it's more acute than that angle, then you're gonna have some problems with overhang in your model. Now here's some tips for being able to hang or take care of overhangs. Now, if you look in the image below, an easy way to take care of this overhang is to just flip the model all around. So say for example, the image doesn't show it here just because the image is flipped around, but say for example you're printing this model at the bottom here. Well, the one on the left is going to have some problems with that triangular overhang on the side here, But if you flip it upside down and you have the floor here, then the printer has no problem being able to print layers on top of each other this way, because it's only, you know, printing less and less on top of the layer that's already there. There's already a support down here, if that makes any sense, as opposed to here, where if the printer's printing layers like this, and you know there's nothing underneath to support the layer that has this section here, then this section will start falling apart, or it won't even print it at all because it has nothing to stick to. Let's see. So another idea for dealing with overhangs is to consider whether or not it should be possible for you to print your object as multiple parts. Meaning you could probably just print the overhang as a separate piece and be able to just put it together with the rest of the piece. So for example, I guess for this, you could print a rectangular prism here and then just print a triangular prism separate and then just glue them together at here, you know, like if they were to be separate, if there were to be like a dividing section here or here, you can just put them together. So, you know, so as long as your piece is still functional and you have all the necessary pieces for dividing the 3D model shouldn't be too much of an issue, you know, but it would be a clever way for you to take care of the overhangs without having any issues. Just make sure that it, you know, it still does what you want it to do. Otherwise, don't risk, you know, don't risk doing things that you're not comfortable with. So here's a link that MakerBot themselves, you know, the people who make these 3D printers, or actually I should say the 3D printer. They're kind of like the Apple of 3D printers. They've been around for a while, and they make, I mean, they're pretty good hardware. They're user friendly, so they're the 3D printers to have. But you know, here's a video that video link that show that, you know, that they themselves have created for you know, as tips for being able to deal with overhangs. So we're going to go ahead and go past that, since we will not have enough time to cover everything in this workshop. So another thing that people run into is geometry issues. You know, a lot of the times people make 3D renders, and what ends up happening is that they don't make shapes that are closed. So let's say, for example, you want to create a cube, but one of your faces is missing. Well, your 3D printer can't read that. It doesn't know what to do with that. The way a 3D printer works is it'll print solid objects that are closed. So, you know, the presence of flat surfaces that are not part of a 3D solid will make your 3D printer impossible for the 3D printer, or your 3D model impossible for the 3D printer to create. And I mean, that makes sense, really. Think about it. The computer's reading this model as as code, not necessarily as an image. So we can look at it and say, yeah, that's a box. But if it's missing one wall, your printer will start printing, but then say, wait, there's nothing here, nothing exists. And then it'll just stop printing because it doesn't know what to do after that. You know, it's a computer. You have to tell it what to do in order for it to do it. Overlapping or hitting geometry. You know, sometimes we make the mistake of creating a box, and then we think there isn't a wall somewhere, but in reality, the wall is there. You just can't see it because it's because of the software. You know, it either makes it transparent so that you can see through the box, or you're zoomed in too much that the face is actually behind you and you don't realize it. You know, simple little mistakes that, you know, everybody makes. But fortunately enough, you know, the software that we'll be using, Google SketchUp, when you create a cube or, you know, any prism of some sort, it'll create it as a closed model. But, you know, the problem comes when we start moving and shifting parts around. You'll accidentally click on a face that you don't want to, and you'll move that face along with whatever you wanted to move, and then you run into the problem of not having a face on a cube that, you know, you accidentally moved. And then what you'll end up doing sometimes is making a face over a face that already exists. Now the computer can't print that because the computer is saying, well, there's already face here, but there's another face that isn't connected to anything, and that most likely ends up happening because you added that face, like I said, on top of another face, but that face isn't necessarily connected to the original closed model. Let's see. So yeah, so you can't print those faces. And you can print faces that are inside closed models because it's not connected to anything and it's hidden, and the computer doesn't know what to do with that. So, finding them can be really hard, but fortunate enough, if you look around, fortunate enough, we have a software where you can maneuver around and look around your models. And if it looks like something's out of place, most likely it is. Sometimes you won't catch it unless you zoom in really, really close to make sure all your edges are connected. But like I said, it's really tricky. You just have to be really careful when building your 3D models. Now, if you think there might be something wrong with your box or your shapes, or you think there might be some hidden geometry, what you can do is click on the object, which makes the object, you can triple click on the object and that makes the object display all its faces like you see on that cube. And you can see there is nothing inside of it. There are no hidden faces. All your vertices are connected with each other and all your edges look fine. So you should be good. This model right here should be printable as it stands right now. Sorry. And actually, let's see. Give me a second here, sorry. Okay, so it looks like we do have some time to watch the video. So we'll go ahead and watch it now.
When you're preparing an object to be 3D printed on a MakerBot, you'll have to look out for something we call overhangs. An overhang is a part of your model that hangs above the surface of the build plate with nothing underneath it to hold it up. If I was making a model of myself with my arm outstretched like this part of my arm would be considered an overhang. The success of an overhang depends on the material, the temperature, and print quality that you're using. But generally speaking, if an overhang is angled at 45 degrees or steeper, the extruder should be able to shoulder each layer of material on the previous layer just enough so that the end result is smooth and accurate. Any overhang that's angled shallower than 45 degrees may result in some stringiness or unevenness that can usually be sanded off later. This massive overhang test by Thinkster is a great way to see the different results you will get when you try 3D printing objects with overhangs. It's designed to test angles 20 degrees through 70 degrees at 5-degree increments. As the angle gets shallower, the overhang becomes less smooth and more stepped. If you're doing your own 3D modeling, it may be helpful to consider overhangs while you're designing. If an angle can be changed by just a few degrees to avoid an overhang, it may be worthwhile to do so. This model of Sappho's head was originally shared on Thingiverse by Luke Chilson. The most difficult overhang on this model is here on Sappho's chin. When 3D printed in this original configuration, Sappho gets a bit of a scraggly beard. Snacks on Snacks did a remix of Sappho's head that split the model in two. Splitting a model in half and then printing it in two pieces and gluing it back together is a great technique for avoiding overhangs. Thingiverse user RichWrap also did a remix of Sappho's head, which improved the chin overhang by just tilting the entire model back 5 degrees on its platform. Learning how to 3D print on a MakerBot is just like learning any new medium, in that it helps to realize that there are limitations, and learning how to work within those limitations can be one of the most creative and rewarding parts of the process. Another good thing to know is that when your 3D model has a horizontal line on top of two pillars, your MakerBot 3D printer will do what we call bridging. Bridging means spanning a gap quickly between 2 points so that the extruded material is strung in a straight line from one side to the other. No matter how small a bridge is, the underside of the bridge will always end up being a bit stringier than the rest of the model, but the following layers usually manage to make a quick recovery. Here's some examples of bridging tests that we do here in the office. As you can see, the longer the bridge, the stringier the underside. If you're making a model with lots of overhangs or large bridges, it may be useful to build your model using single material breakaway support. When you choose to add support to a model, your MakerBot will extrude a loose mesh-like material under any overhangs. The support is made of the same material that the rest of the model is made of, but because of its mesh-like nature, the support will be just strong enough to hold up the model's overhangs and just fragile enough to be pulled away from the model when the model is complete. Getting the support material to peel away from the model can be a bit tricky. We recommend using needle nose pliers and then twisting it off the model like this. Work slowly and be careful not to break any of the delicate parts of your model. We're currently working on a number of improvements to support that should make the removal process easier. Stay up to date with the new releases of MakerBot Makerware and your machine firmware so that you don't miss these updates. The last bit of vocabulary I have for you is rafting. A raft is a single layer of extruded filament placed in a thick grid-like pattern at the bottom of your model that can be peeled away when your model is complete. A raft is useful when you're having trouble getting your model to stick to the surface of your build plate, and you'll always want to use a raft when you're printing with support.
So there you go, just some tips on how to be able to build your 3D models efficiently so that you can reduce the amount of work you need to do when dealing with overhang. Now, again, we want everybody to be able to share their work through CSTEMbreak.org so that we can see your work and we can, evaluate it and, share it, with the community, with the CSTEM community. Go ahead and take images, upload them to CSTEMbreak, and communicate with each other and other students and from other schools there. We've already seen some students doing that, and we would like to see more students, just incorporating that into their CSTEM program or school. Thanks. Before I go, actually, sorry. I should mention that we're going to go ahead and start taking submissions for 3D prints through CSTEMbreak. We'll go ahead and I'll go ahead and set up a page and with a reminder at the front page to where you can turn in your 3D printed models from Google SketchUp. This way we can I can go ahead and take a look at your 3D printed models and let you know ahead of time if your 3D printed model is printable or not. Again, you want to make sure that you avoid overhangs, as much as possible, and we want to make sure that you, don't have any hidden layers or hidden faces or overlays. We're gonna go ahead and have set a deadline for March 1st for your submissions. That way, that gives us enough time to print your 3D printed objects if you don't have a 3D printer, and then send it back to you so that you can practice with it before the day of competition. But other than that, thanks again for joining me. Again, my name is Orlando Benitez. You can reach me at CSTEMbreak through my CSTEMbreak account, or email me at media@cstem.org for further clarification. I will have a couple minutes in the chat box below to answer any questions regarding 3D printing. Again, Happy New Year, and I'll see you for the next session. Hello everyone, this is Orlando Benitez. Thank you for joining me for the third Saturday workshop on January 10th, 2015 for BristolBots, Ingenuity at its Funnest. Now for those of you who don't know or are just joining us, my name is Orlando Benitez. I am the graphic and web designer at CSTEM. So I'm considering myself pretty tech savvy, and I also love to tinker with things, which is why I am your trainer for the BristolBots. But again, I'll say what I say in every other workshop. You don't need to be extremely tech savvy to be able to build and work a BristolBot. They're fairly simple to build and they're fairly simple to use because they are what, essentially simple machines. So, for those of you who don't know, we are currently in cycle 4, January 10th, and we are in the design prototype stage. So at this point, you've gotten a good idea as to how to build a BristolBot and what they look like. So for this Saturday workshop, we're actually going to go ahead and build one. Now, since I don't have the tools to personally build a BristolBot, I was able for the remainder of the time here, we're going to watch some videos that I think stood out as a very useful that stood out as very useful videos for how to build a BristolBot. So you'll get to see, nonetheless, how to build a BristolBot, even though I do not have the materials myself. The first video that I want to show you is a video about this guy I found on YouTube. He actually makes BristolBots, but he makes the design different. So normally we build BristolBots using a toothbrush, hence the name BristolBots. But because because this one stood out to me as unique, we're gonna go ahead and watch the video where the guy doesn't use brushes, but instead uses these little like wires or toothpicks, very like thin wires of metal, as you can see here, to build the legs and antennae of what it's supposed to be, a bug. Let's take a look. And I should mention that he used the motor on an old cell phone to make the BristolBot. Let's see, here we go. So there you go. So what he did was he was able to make a frame for the actual bug, and then he used tape to actually build the shape of it. You'll notice towards the end he used a battery and a couple wires to connect the motor that he took out of the cell phone, so you can make the robot walk. Now this next video shows off a BristolBot, a traditional BristolBot, in the way that we know it, as in, in that it actually uses the brush head, so that you can get to use it as legs so that it can get the robot to move. So let's go ahead and take a look at this one. So there you go. That's a simple way of creating a Bristol bot at home using just a couple of tools. It does require for you to use some appliances. So I do recommend there is some adult supervision around. We don't want our kids messing around with pliers, obviously. But it's a fun project for you to be able to do at home. Now, the Bristol bots that we have provided for you are kits, so they should be able to come together quite simple. And in fact, they come in with instruction on how to build them, but that does not mean you're limited to the design that they have created. Again, you do get some points for creativity, so go ahead and add your own flair to your Bristol bots, but just make sure again that you're not restraining yourself from or putting yourself at a disadvantage because you will be putting these on a ramp or incline. You do not want your Bristol bot to stumble on the some of the obstacles. Again, I'm going to go ahead and leave some resources here on the PowerPoint. These are just some resources as to where you can buy Bristol bots, Bristol bot toys, or how to build Bristol bots, or links on how to build Bristol bots, like the videos you just seen before. Now, once again, we'd like to emphasize that we want to see your work. So, go ahead and upload your images onto System Break, and or I guess I should start by saying that you should join System Break if you haven't already. It's a social media. It's 100% free. You're still more than welcome to join the social media page. And here you can upload your images and show off your work. We encourage everybody to upload images of them and their work, but it's not mandatory. It is something that we want you to do, but you don't have to do. I know a lot of people might have some projects that are super cool and might give them the edge in the competition, so they might not want to show them. But go ahead and just show images of you and your team working. You don't necessarily have to show your project, but just make it fun. Obviously appropriate, but make it fun. Again, thanks again for joining me. If you have any further questions, my name again is Orlando Benitez, and you can reach me at my System Break account, or Orlando Benitez, or to my email address located at the bottom of the screen there, media@system.org. Thank you, and Happy New Year.
is a sculpture I made, which is a way of kind of freeing a form into an object that has different degrees of freedom. So it can balance on a point. This is a bronze ball, an aluminum arm here, and then this wooden disc. And so the wooden disc was really thought about as something that you'd want to hold on to and that would glide easily through your hands. And the aluminum is because it's very light. The bronze is nice, hard, durable material that could roll on the ground. And the inside of the bronze bowl, there's a lead weight that's free swinging on an axle that's on two bearings that pass in between across it like this, that counterbalance this weight, so it allows it to roll. And the sphere has that balance property that it always sort of stays still and looks the same from every direction. But if you put something on top of it, it misbalances it, and so it would tip over. But in this case, because the interior is free swinging in relation to the sphere, it can stand up on one point. And then there was a second level to this object, which is that I wanted it to convey some proportions that I was interested in, which is the diameter of the moon and the diameter of the Earth in proportion to each other. I was exploring really early on, wanting to make things float in the air, and I thought up a lot of ideas. This is a sculpture that I made that's it's magnetically levitated. Thing is, it's slightly dangerous, and normally it's sort of cordoned off when it's in a museum. But it's let's see if I can manipulate it a little bit without. Oops. So this is just floating on a permanent magnetic field, which stabilizes it in all directions, except there's a slight tether here, which keeps it from going over the top of its field. It's sort of surfing on a magnetic field at the crest of a wave, and that's what supports the object and keeps it stable. I think we could roll the tape, Ed, and then I have a sort of a collection of videos that I took of different installations which I could narrate. This is a sculpture of the sun and the earth in proportion, representing that 8.5 minutes that takes light and gravity to connect the two. Like this. So here's the earth. It's a little less than a millimeter. That was turned to solid bronze. And here's a similar sculpture. That's the sun at that end. And then in a series of 55 balls, it reduces proportionately. Each ball and the spaces between them reduce proportionately until you get down to this little earth. This is in a sculpture park in Daejeon. This one is about the moon and then the distance to the earth in proportion also. This is a little stone ball floating, as you see the little tether, but it's also magnetically levitated. And then this is the first part of, this is 109 spheres, since the sun is 109 times the diameter of the earth. And so this is the size of the sun, and then each of these little spheres is the size of the earth in proportion to the sun. It's made up of 16 concentric shells. Each one has 92 spheres. And this was in the courtyard of a 12th century alchemist. And I was thinking of the sun as a kind of the ultimate alchemist. So this again is on the subject, a slice from the equator of the earth, and then the moon in the center, and it's floating. This is in France. This is in Sapporo, and it's balancing on a shaft and a ball right at the center of gravity, or just slightly above the center of gravity, which means that the lower half of the object is just a little bit more weighty. So you can see it rotating here, and it weighs about a ton or over a ton. It's made of stainless steel, quite thick, but it's being balanced like that in equilibrium. It's susceptible to motion by the air currents. This is another species of work that I do. These are arrays, and these spheres are all suspended, but they have magnets horizontally in them that make them all like compasses. So all the red sides, for example, face one direction south, and the blue side, the complement, faces the other way. So as you turn around, you're seeing different colors. So this is based on the structure of a diamond. It was a diamond cell structure was the point of departure, and then there were kind of large spaces in the kind of the hollows between the atoms, and so I placed one more element inside of each one of them. And these were white spheres, and then I had video projectors that were projecting intermittently onto the spheres, so they would catch parts of the images and make sort of three-dimensional color volumes as you walk through it, through the object. This is something I did of a tactile communication system. It was the idea of isolating the tactile component of sculpture and then putting it into a communication system. This was an idea of moving a sculpture, a ball that would be directed around the room by a computer. This is a clock I designed. It has Buckminster Fuller's Dymaxion map edited here. It turns once per day in synchrony with the Earth. And then this is like projects that are harder to build, something that would, this has a diamond-bottomed lake. So it's a floating island with water, fresh water, that can fly from place to place, be grown, I suppose, with nanotechnology in the future sometime. In the course of doing my work, I sort of have a broad range of interests, and some of it is just the idea of creating media as a sculpture, something that would keep the sculpture fresh and ever changing by just creating the media that the sculpture is made of. And I had a lot of always interested in the concept of a crystal ball and the idea of that you could see things inside of a crystal ball, predict the future, or a television set where it's sort of like a magic box where anything can appear. And I had thought about a long time ago, sort of in the late 60s when I was just starting out, under the influence of thinking about Buckminster Fuller's grand project for an electric globe across from the United Nations, and other things that were happening in the space program at that time, and Whole Earth catalog, things like that. I was thinking about a mass-produced spherical television sets that could be linked to orbiting camera satellites. And so if we could roll the next film here. This has evolved over the years in a lot of different iterations, but this is the current version of it is a flying airship that's about 35 meters in diameter, about 110 feet in diameter, and the whole surface of it is covered with 60 million diodes, red, blue, and green, that allow you to have a high-resolution picture visible in daylight. And so I came with a plan. I brought it to Paul McCrady's company, Aero Environment, to do a feasibility study, and they analyzed it and came up with a lot of innovative ideas of how to propel it. So we have a physical plan of how to make this actually happen. And this is the control room inside of the ship. And the idea of this Air Genie is it's something that can just transform and become anything, and it's like a traveling show. It has speakers on it, and it has cameras over the surface of it, so it can see its environment, and then it can mimic its environment and disappear. And here the legs are retracting, and the cabin is open or closed as you like. Weighs about 20 tons. It has onboard generators, can generate about 1 million kilowatts in order to be bright enough to be visible in daylight. And the idea of it is to make a kind of a traveling show. It really would be dedicated to the arts and to interacting. And there would be on board a crew of artists, musicians that would allow the thing to become actually kind of a conscious object that would respond to the moment and to interact as an entity that was aware, that could communicate. And it's completely silent and non-polluting. It has electric motors with a novel propulsion system. It could be, interact with large crowds in different ways. Primarily, I would be interested in how it would interact with, say, going to a college campus and then being used as a way of talking about the earth sciences, the world, the situation of the globe. The default image on the object would probably be a high-resolution Earth image, but then one could interact with that and show plate tectonics or global warming issues or migrations, all of the things that we're concerned with today. And then at night, the idea is that would be used as kind of a rave situation where the people could cut loose and the music and the lights and everything. So it could land in a park, for example, or this could represent a college green. And then it would have a corresponding website that would show the itinerary of this, and so interacting with the same kind of imagery. And then it would also be able to be an open code so people could interact with it. It would be a forum for people's ideas about what they would like to see on a giant screen of this type. And so that's pretty much it. Okay, thank you.
Good morning and welcome to the C-STEM Challenge. I'm Sarah Trotty and I'm happy to share with you the Mural Challenge for Energy Infrastructure, Wind, Oil, and Natural Gas. Of course, we've been talking for a while and just have here again some little information about my experience working with murals at Texas Southern University. Our current cycle is that of the design prototype. This is where the students actually design a model or a prototype of their C-STEM Challenge project solution. Hence, we'll enlarge the design from the earlier sketches that were done. This cycle utilizes that information that was gathered during the previous research cycle. It takes a look at the best aspects of the sketches that were done. At this point, the students are going to select from those combination of sketches to come up with a final look of the desired mural. That look will be in sketch form, which we will call your prototype or your model. And then once it's in its form, it will be used to enlarge to the final aspect of the mural itself, which will be on the canvas that was already prepared. I recommend that this piece, this sketch, this enlarged sketch, be proportionate to the completed mural size. So maybe approximately 1/10 the size at the very least, so that when you look at it, it's easy to create that larger view. I want to remind you that this verbal exchange between all the student participants, it remains crucial throughout the completion of the competition. So talk to one another, make decisions together, and then work together. I also want to remind you of the expected outcomes for this mural activity. We've had these each time, so I'm just going to touch on them again. The students and teachers will engage with professionals as much as possible that connect STEM industries with classroom learning. This is very important because you'll develop everlasting friends and supporters of your school project. You are expected as students and teachers working with them to learn about innovative and relevant content and tools and resources that will help the students later on to become great leaders, help them utilize their creativity, their critical and solutions-driven thinking. This is really important to the overall experience. It's not just a project, but it's a lifelong experience. Now, in terms of making the mural itself and its framework and what it's actually intended to do, each level, elementary, which we will call K through 1 and 2 through 5, and middle and high school students will reflect on this year's theme. And this is what the seniors are going to do as well, high schoolers. But the energy infrastructure, again, wind, oil, and natural gas. Everyone will conduct research. We should have completed the research by now. And then their research experiences will help them in the production of the actual mural. Not only is the mural produced, but a written document experiences will help them in the production of the actual mural. Not only is the mural produced, but a written document
Good afternoon and welcome to the documentary filmmaking training. I'm your trainer, Lori Mitchell. Happy New Year, guys. Okay, so let's get started. My system is a little slow today. Okay, so this is the design prototype cycle. And in this cycle, students will design their prototypes of the CSIM Challenge project solution. So what we're going to focus on is filming and set design and film positions, which would be directors, assistant directors, cinematographers. And for set design, pretty much plain old cinematography. And we'll get into that. Now, last time we spoke about how to create an equipment list and how to gather additional footage. So your students should be in the process of looking at photos they want to add. Possibly they've gotten the people who they want to interview. Outline should be organized. So far, basically how you want the documentary to look. You probably should have had some of your students research documentary films. So that's where you should be at this point. So now we're going to get into set design. Set design, also known as the order or production design, of creating a look and feel of the environment for your story. So it's just making your story seem authentic. For example, I have a short film entitled Juke Joint Blues, and yes, I do know Juke is spelled J-U-K-E. There's a reason behind that. If you want to watch it, I think that adults watch the film, but sure, you can send me an email. If you are a teacher, you can watch that film. No students. But it was set in 1958, and I really wanted to get that look. So I did the best that I could, and I took a restaurant in the 5th Ward area of Houston, Texas that was filled with booths, and I redecorated, took all the booths out, put in chairs. Then we also, for the dressing room scene, I used the spare room in my home, and I'll show you. On the next slide here, this is the nightclub scene at the top. So I had my people dressed up in their best 50s attires. I researched that for 9 months on how I wanted my film to look. I used the first photo that you see here. The guy looks like he's behind the bar. That actually was the cash register. The cash register is behind there. At the bottom, again, that is a separate room where you see the bottom photos, the last one or the second photo at the bottom, that red curtain, that is a closet. I had my actors stay in the closet to make it look like they were coming out of the door of the actual club. And again, if you want to watch the video, just send me a personal email and I will send you the link to that. But to make your documentary have the feel that you want, you must research how you want something to look. And that's all set design is. And so how do you design a set for a documentary film? Because what I just showed you, that was just for a short film. That's simple and easy. But there's obviously a lot that goes into set design, picking a location, the room decor, and the depth of your image, meaning what you will use, what cameras you'll use to get that specific look that you're looking for. So, your location. Picking a location, in many situations, your location choices may be limited. If you're doing a documentary about an earthquake in Haiti, it's pretty obvious where you'll be shooting. But if you're shooting a corporate video where you will be interviewing key executives, you may have a number of locations. Their office, conference room, a large lobby, maybe a library. And if you have an opportunity to pick location, you want to keep in mind the audio, like traffic, the noise, computers humming. Sometimes you can hear the air conditioner, and we went over those things with a boom mic. You also may want to get a wind diffuser for your boom mic, and sometimes in camera, if you're using one of those DSLR cameras that we spoke of last time, they have a wind diffuser setting on there. So definitely your location, your decor, which is what I love to focus on because, like I said, I am big on making your film look authentic. So once you've picked your location, don't be afraid to move the furniture around. If necessary, adjust the picture frames. I know the documentary film that we were working on for Sickle Cell, there was too much white space behind one of the people we were interviewing, and so we took all of the picture frames that we could find in that location, and we tried to make it have a certain type of layered image, and we'll get into that shortly, a little more in the next few slides. But adjust picture frames, plaques, awards, things like that. Having a busy background, lots of items with lots of different colors and shapes could be distracting from the interviewer. So also you want to be careful of that. You want your interviewer to interviewee to be the focus, but you still want your area to look nice. So if you're focusing on oil and gas, maybe you want to have a drilling rig in the background, a photo of a rig behind one of the people that you're interviewing. Or, maybe you want to interview outside by a rig, an oil rig. So, you could think of things like that. And this is a little slow. Oh, okay. Her image early with your camera lens. And we're going to go into different looks, and different looks create different stories. So unless there's absolutely no choice, avoid interviewing subjects up against walls or bookshelves. You don't want to have a flat view. See, in this picture to the right, the bookshelf is in the background and it's slightly out of focus. I'll show you different cameras to use for that. Lens, not cameras. So you want to have your film look crisp. And so here are the different lenses that you could possibly use. You can use a prime lens, which is a fixed focal length. It cannot zoom out and it cannot zoom in. It's just a lens that just stays the same. Therefore, when using a prime lens, every time the filmmaker wants to get tighter on the subject, you have to physically move the camera. So it won't zoom in, it won't zoom out. The lens is fixed, it stays the same. And if you want to get a different look, you have to move the camera. You cannot change the zoom. Telephoto lenses are longer than average in comparison to a normal lens. And a normal lens is just, we'll get into that. Let me not go ahead of myself. I'm sorry. But, or the human eye lens, and we'll get, so the telephoto lens, it can really get it tight on the subject. It's great for zooming. The image is, it's normally a really, really long lens. That's the best way that I can describe it, because I put this definition here, but I'm trying to make it as simple as possible. But the lens, if you ever see those really long lenses, those pretty much are telephoto lenses. And the wide angle lens, which is just the lens that'll give you a shot of everything that your eye possibly sees. It gives you more of a range of the subject that you're focusing on. And the normal lens, it's like I said, it's halfway between the telephoto lens and a wide angle lens. that also gives you what your eye sees, but the wide angle lens gives you a little more. And I have examples so that you can see, because I know just by saying what a lens is, it's kind of confusing if you can't see the kind of images that it's portraying. So let's see here. Sorry, my system is slow. Okay, so the prime lens image. This is the lens I was talking about. That's the fixed lens. You cannot change anything. But if you notice, I love prime lenses. Those lenses give you awesome imagery. And as you can see, the leaves are in focus, but all of the background is out of focus. That's beautiful to me. I don't know about you guys, but that's awesome. And that is a 28 millimeter lens. So if you want to start researching some lenses to give you those certain kind of images, I've placed what type of lens give you those images next to the picture. So the next lens that you're going to see is a telephoto lens. And it's, again, that's the long lens, so it's giving you everything is in focus. And that's a 70 through 300 millimeter telephoto lens. And that's a beautiful picture as well. And you see how far away they are. And sometimes those images, you're actually closer than what the lens is showing you, but it gives you a different feel. It looks like a long journey. So this picture is pretty much telling a story. I could see a farmer walking all the way to that home, you know, after a long day in the field or something. So definitely the lens that you choose tells the story for you. Okay, this picture was taken with a wide angle lens, 10 millimeter. And as you can see, this is giving you the view of what it was seeing if you were in the back of a church. This is pretty much what your eye would see. You may see a little more, but it's giving you a good view. And wide angle lens, I think, are the best lens to use for an establishing shot, like the beginning of your film, or where you want to. And establishing shots are simply shots that tell you where you're located. So in the beginning of a movie, when you see that they show a house, then they show what's going in the house. You always want to start whatever scene off with an establishing shot. And wide angle lenses are great for that. And storytelling, of course. Now your normal lens, again, it gives you what the normal human eye views. And this is a view of someone taking a shot with the normal lens, 28 to 40 millimeter. It looks like they probably were kneeling down or squatting down when they took this shot because it's at a lower angle. But it is giving you a view of what you would see if you were physically squatting down with that lens. So out of all four of those types of lenses, as a documentary filmmaker, depending on what you're trying to tell in that story or the emotion that you're trying to present, that would be great for you to use one of those. And that's how you decide on what kind of lens you want to use to tell your story. So whose responsibility is it for the look of the film? And this is when we get into the actual film positions, or crew positions rather. You know, there's a thing called above the line and below the line crews. And above the line are normally this list here, where you have your director, not necessarily your casting director, but your director, your cinematographer, your assistant director, which I don't have on the list, and your camera operator. So your director is responsible for overseeing. And I know I have this really lengthy, but I'll give you my simple definition of it. What a director normally does, they go over the script, they line the script up to show where they want to do their blocking. They is responsible for the interviewing during the documentary process. Sometimes they are responsible for the location scouting, but you'll sometimes have your own location scouts for that, but the director gives you the structure of the film. And then when the filming begins, that person, the actors in the right way, or guide the interviewees in the right direction, where they ask the questions and they get them to create or evoke certain type of emotion for the camera. Casting directors are normally the persons who go out and find the people to interview. Or if you're doing a regular film, it's like an interview. They have a casting call and they decide on who's best for the script. The director of photography, which is called the DP or the cinematographer, that's the person that has to know the lens. That person should know every lens that I mentioned earlier. They should know those things because they want to be the ones to give the film its look. So they work hand in hand with the director to say, hey, this is what the film is going to look like. These are the colors that we're going to use. This is just the imagery that we're going for. This is what this person's interview is going to look like, the whole scenery. So your cinematographer or DP will be responsible for that. Your camera operator sometimes can be both the cinematographer and the camera operator. I like to do separate because for me it just seems like when you have a camera operator, they need to focus on the camera. And the cinematographer needs to focus on making sure everything looks great. So that's why I prefer to have separate, but you may have someone that's just that good, and occasionally I have had that where they're just that good where they could do both, but I've had better experiences and better film look when I chose separate people to do those two tasks. So you also want to keep in mind to have a gaffer, a best boy, and a lighting technician if you're going to use professional lighting. And the reason why I say this, especially with working with children, those lights get very hot. I would suggest to work with fluorescent lights instead of those professional lights. I'm meaning fluorescent lights like the studio lighting because they don't get as hot. You always want to have the gaffer because the gaffer can organize things. The best boy can help pick up things, cords, and the lighting technician will make sure that everything is set up correctly. So filming, being on set can be dangerous. So because we are working with kids, we want to focus on safety. So I personally would suggest the fluorescent lights if you're going to use professional lights. Because the fluorescent lights don't get hot, but when they do stay on for a while, they'll pop if you touch the actual light bulb. So both are dangerous, but the children won't get burned with the hot professional lights where you can see the smoke coming from the light. So I just would prefer the fluorescent. That's just my professional opinion if you guys decide to use that. And natural lighting is always the best way because with the natural lighting, you can get everything done. Okay, guys, I hope I didn't go over my time, and this is a wrap. That's all that I have for you today. Our next training will be Saturday, February 7th. I will stay connected to you. If there are any questions, you can reach out to me on CSTEM Break. And again, Happy New Year, and thanks for attending.
All right, everyone, and welcome back to the very first of our CSTEM challenges of 2015. My name is Alicia Garcia here with Houston Center for Photography. Let's take a quick look at where we are in the challenge. We are just about in the very middle of where we need to be. So if we look, we finally get to make a prototype. And I'm sure we all remember what we went through last year. But keeping in mind that this year we're focusing on the frame being a different size. So when we make prototypes, that is something for you to double check. Make sure that your students are not making the wrong size. And my next slide very simply says, you are to design prototypes, and I've underlined the letter S, of your CSTEM solution. There is no possible way to simply make one prototype. What happens if your student is using the wrong glue? They're using material that will deteriorate before the actual challenge can be shown. We need to make sure that we take positive action so that your students can move forward with your challenge. So today we want to emphasize the process of building the frame. Since prototypes will be made, I don't expect that there will be a final result by any means. But with your close-up photography, we want to find the areas that you've modernized and take those photos of what is clean, generated, renewable energy. Now, in the previous challenge last year, the rules were different for what the frame size was. This year, so that we're not going in autopilot, the frame is no bigger than 8 by 10 inches. The photo itself cannot exceed 8 by 10 inches. So what I have gone through and made some little illustrations about how we can creatively look at how to look at the frame. So in this photo, this little diagram, the brown edge is, let's pretend, a wooden frame. And the white area is the glass of the frame. So if we went into Hobby Lobby or Michael's and we bought this frame, this is what we would be looking at. This is a physically constructed, we go in, pay some money, standard frame. If I went and put a photo in that frame, it would look just like this. We're illustrating that my photo is on blue paper. That is in the standard world of things, where you buy a frame, put your 8 by 10 photo in it, and this is what we get. But where's the challenge in that? So where we ask for you to put your thinking caps on and get smart and creative is that 8 by 10 is the maximum size a photo can be. Nobody says the photo can't be as small as this example here. So let's say you have a student or your school has limited funds or something happens and you can only work with 4 by 6 pieces of paper or 5 by 7 pieces of paper. But you got told what you turn in has to be 8 by 10. If you went to a store and said, I have a 4 by 6 photo, this is a little blue piece of paper, it does not fit well, doesn't look aesthetically pleasing in a standard frame. But lucky for you, we're not making standard frames. You could, in fact, construct out of all your own material a frame that is, in fact, 8 by 10 and surrounds your little 4 by 6 photo. That is a possibility. Nobody says that bigger means better. We want a very good photograph, just as long as you don't exceed the maximum size. That is what we want to emphasize today. So if we look at some examples of the really close nature, that quiet, contemplative photo, this is the absolute extreme. People have framed with mats all sorts of ways of making little tiny moments happen. So we're looking at a very teeny tiny photograph within a custom matted frame. Now, with your students, are they using custom mats and having that done? No. But where that black frame and that white mat meet, imagine that's all found material. and its dimensions happen to be 8 by 10. I mean, you can go to anybody's office or, gosh, I can go to any one of my friends' houses, and I'm sure I can find a frame that looks just like this. So the act is, nobody's forcing you. If you don't have the ability to print a large photo, you don't have to make that photo that large. In fact, you might have a lot more creativity if you maximize the idea of communicating the photo surroundings via a larger frame. Larger in mass of the frame, but not in the inches that it takes up on the outer perimeter. So, example here, little tiny photo, really thick, big mat, and it's still an 8 by 10 frame. So there are so many ways for you to be able to have your students just dream. And that means they can draw, they can glue, anything they find in their surroundings. All it being safe, of course. If you find anything that is not safe material for them to use, please, we don't want any sharp objects at all because we are dealing with elementary school. But anything else that they see, please let them. And if it means having a really loud moment of a really large photograph of 8 by 10 inches, or a photograph that's really tiny and is a quiet moment, those are things to think about. And if you went somewhere that was really loud, maybe the photo should be big. If they went and found a place in the city that happens to be very quiet, that's also important. So how do we make the prototypes? A prototype is the early sample or model or release of a product built to test a concept or process. This would make a lot more sense if we were architects. That before we build the building, we actually make a model of it. So does the prototype have to be to scale? No. But if you have a student that wants to glue two materials together and you know that that is impossible, let them try and say, uh-oh, we better try another idea because the first little prototype you made isn't necessarily working, so we need to get some better materials. And of course, you can always have multiple prototypes, which I always encourage, and multiple drafts to your photos. Again, so no one says you have every draft you have to make with your student has to be 8 by 10. You can make teeny tiny little photos if it means, one, you're saving money for your school, and it's easy to just churn them out. You can just go to Walgreens and just have them print off just a bunch of little 4x6s. They'll feel special. You'll have lots of things you can pin up in your classroom, and everyone can feel like they're getting somewhere. So of course we take lots and lots of photos. It takes many, many photos to get the quote-unquote top 5. And I'd say that's the idea we're going for, is that when they start making prototypes, we should have at least 5 ideas from all the sketching and storyboarding that we've been doing. Have 5 ideas to get you to finally pick that best number 1 photo that should be brought to George R. Brown. And tell your students, it takes even masters, professionals, it takes us a lot of photos. It's not because we don't know what we're doing. It's because we do know what we're doing and we know what we want to find. So if you want to have a good result and an award-winning project, well, that's going to take a little bit of time. So sometimes it's hard, whether you're really young, elementary school age, or you're in high school, to turn your computer off and turn your TV off and just go outside and enjoy the scenery of Houston. Enjoy your neighborhood. Tell them that it's so important to venture out with safety in mind, but venture out and find really great areas that could help them with their project. But exploring the world with the camera is so much different and more beautiful than just walking around. Because you're stopping and taking quiet moments to show the world what you see. Because even though the eyes are the camera to the human soul and the body, the camera is the mechanical representation of the eyes. So we can definitely move forward and help your students out by just letting them understand the beauty of a camera. I always like to show these photographs, the great master printers. Imagine in the darkroom when photos were made, and there are lots of drafts, lots of edits and scribbles all over a photograph of where photos need to be darker or brighter or lighter to get a master print. So imagine an edition of 10 photos that had all of that work on the left side had to be done. People worked for a very long time to make one photo, much less two. And classic photos of Audrey Hepburn were not just a one and done. These took lots of time. And just because we have digital cameras doesn't mean it's any quicker. So we should spend lots of time, because the greatest people that ever lived while holding cameras took a lot of time. And it wasn't because they didn't care, it's because they did. Muhammad Ali, all the processing that went down on his photo. So a lot of TLC, a lot of tender love and care. But another thing just to keep in mind is the idea of what we like to emphasize to the students. And we could probably figure out a better shorthand for it. But in the photo world, we call it the decisive moment. That moment that you decide to push the shutter on your camera, click the camera button on your cell phone, and why you as a person chose not to take that photo a second before or a second later. That in that 1 second, you get a photo just like this, where somebody is running and they're neither foot is on the ground, and it looks like they're floating. Take that photo a second ahead or a second behind, we're not getting the same result. And there were a lot of photos taken to get this one. Same can be said for sports photography. People moving around, jumping for the Olympics. I mean, there's not a lot of opportunity to catch someone in midair. Or surfing. I mean, we don't know if they have 10 seconds or 1 second while they're riding away. But it's your job to be waiting with your camera. And that is one of the most important things, is to always be prepared. And that's just a really strange thing to have to teach children, because they're so used to having cell phones around. But to carry a digital camera is a little different. That type of preparedness and preparation is something that will take a little while longer for them to learn. So if you have any questions about the frame, or you've had questions arise from your students, please join me at CSTEM Break, and I will answer any questions that you need to have solved, or we can troubleshoot together. And I look forward to seeing you next time, or maybe not seeing, but speaking with you. Thank you very much.
Welcome to Everyone is an Artist and Engineer, 2014-2015 Energy Infrastructure, Wind, Oil, and Natural Gas VEX Robotics Teacher Training for Middle School.
Welcome to the 2014-15 C-STEM Challenge, where everyone is an artist and engineer. This year's focus is energy infrastructure, wind, oil, and natural gas. And this is the Mobile Tech Challenge workshop series. This is cycle 4 of our Mobile Tech Challenge workshop series. Before we jump into today's session, let's do a quick review of session 3. During last month's workshop, we focused on 3 critical exercises that will prepare us to move forward. The first one is questioning. So hopefully you've already gone through the exercise. You've answered all of the questions that would allow you to collect the information you need to move forward into cycle 4's workshop. Hopefully, once you completed the questioning, you took a moment to reflect as a group, to identify anything that may have been missed, any questions that maybe weren't asked, any ideas that weren't fully examined. Hopefully we took time to do that. And the final exercise was collecting our resources. So hopefully we've gathered everything we need, all of the resources, all of the tools. We've done inventory on our kits that were provided during the orientation, and now we are ready to move forward. Okay, so moving right along. The focus of today's session is prototype design. We will focus on a short process that gives you the ability to develop a prototype and test it. The simple process that we've identified is called rapid prototyping. Rapid prototyping involves several iterations of a 3-step process. This process will allow you to continue to shape and to mold your prototype until you get to the desired state where you have a product that's presentable at the C-STEM Challenge. So the 3 steps in the rapid prototyping process include designing your prototype, reviewing your prototype, and then taking a moment to refine your prototype. So let's take a closer look at each step. So step number 1, prototyping. This is where you convert your concepts, your user features that you've developed and established, and the descriptions into a mock-up. This mock-up will then allow you to see your product in, yes, an unfinished state, but it will give you an idea of what you're working with. So once you've designed your prototype mock-up, you want to take the opportunity to review it first. Then you want to share the prototype design with users, have them evaluate it, and give you feedback. Now that we've taken time to review the prototype design, we have feedback. I'm sure we provided feedback ourselves about the design, the features, the functionality of the prototype design. And once we shared it with additional users, then I'm sure they provided feedback as well. So what do? We take that feedback and we go back to the drawing board because we've got to make additional improvements. This is just the first iteration. So we've got to go back through the process again. And what that will do is it will give us the opportunity to perfect our prototype design. So now it's time to take a look back and review the 3 steps in the process. So as a review, the 3-step process is called rapid prototyping. The first step being developing your prototype design. The second step being to review that prototype design, first internally, and second with an identified user group that can give you the appropriate feedback. The third step is to actually take that feedback, go back to the drawing board, and refine your prototype design. And so, if you remember back in the onset of this workshop, we talked about rapid prototyping involving several iterations. Well, an iteration is essentially going back through the process of those 3 steps again until we get the desired design and output that we're looking for. So I want to thank you guys for attending today's session. And now it's time to head over and log on to the CSTEM Break chat room. I look forward to seeing you there.
Hello, everyone, and welcome to Everyone is an Artist and Engineer. CSTEM. November 15 training, energy infrastructure, wind, oil, and natural gas, VEX robotics teacher training for elementary. Today's outline is going to be consisting of pairing the VEX Cortex microcontroller and the VEX joystick. We're going to cover some topics of what is pairing, components needed, VEX Cortex explained, VEXNet joystick explained, step-by-step instructions on pairing, option 1 and option 2. What is pairing? Pairing. The joystick must first be paired to the Cortex microcontroller before they work using the VEXNet keys or the USB cable. This process will be completed each time you use a joystick or Cortex with a new mate. A joystick can only communicate with a Cortex that has been paired with. During the pairing process, the ID from the Cortex is transferred to the joystick, thus mating the two units together. Components that you will need for the pairing: a VEX 7.2 volt battery, fully charged, 6 AAA rechargeable batteries, a VEXNet ARM Cortex-based microcontroller, a VEXNet joystick, and 2 VEXNet keys. You will also need some motors if you want to test the pairing before you build your robot. And the motor controllers. VEXNet Cortex explained. To give you an idea, what are you looking at? You're looking at the Wi-Fi key in the middle, which is the VEXNet key that we've been talking about, 802.11.g. Transmits the information to the joystick using wireless signals. You can also insert the USB out there in the same area. Going clockwise, you're going to have serial communications for elementary. Don't worry about this. You will be using motors in your kit, so you will only program using ports 2 to 9. So if you want to change a motor port later on in your programming, you got to make sure where you're connecting the motor controller, and then you're attaching the motor to that motor controller. You have to know exactly what port you've inserted the motor into in order to program your robot. By default, once you pair, you're going to have ports 3 and 5 automatically available to run your motors. Battery, 7.2 battery gets inserted here. Digital inputs, do not worry about it. This is for your sensors for middle school and high school students. And analog if you have analog sensors. A side view of the Cortex. You have the on-off switch, the main power port where the battery gets inserted, backup battery port for Wi-Fi communications in case your battery runs low. It will give you a few minutes to actually communicate with your joystick before it completely dies. Configuration switch for special procedures. Don't worry about this. It will not be used. And also the 7 millihertz crystal, or megahertz, I'm sorry, 75 megahertz crystal interface. It will not be using. These are plugs, plastic plugs that allows you to keep the motors in place. Okay, explain the joystick. You're going to have 8 buttons on the top, 2, 3, 4, 5, 6, 7, 8, 2 XY analog keys. If you can take a look at the numbers, you have 1 and 2 on the right, 3 and 4. And when you program these analog joysticks, that's where the numbers you're going to be manipulating in your programming code. Your power switch, 6 AAA batteries get installed under here. You have to remove a small Phillips head screwdriver. And it's also a 3-axis accelerometer built in with this joystick. You have 4 buttons on the front side, and this is your programming interface. We'll talk about it later. And where you plug in your USB key, so the other key will be right underneath here in this portion. For a view of the button status buttons, you have the first one on top is your joystick. It will followed by the robot battery status. How's your robot doing? This is your cortex responding to your joystick, and the communication link between the two, if they're being communicated or not. And finally, your game status. A green battery, it's good charge. A yellow battery means it's dying, and when you see any red buttons, that means it's dead. On the communication side, green VexNet COM established, yellow is searching. Lights on the controller and the joystick are the same. They should match the cortex and the joystick. Pairing instructions. Start by connecting the charged 7.2 volt battery to the cortex and inserting the key. Add the batteries to the joystick by removing the screw cover and install the batteries. Remove the screw in the middle and insert the batteries. After that, install your VexNet key, as seen here. Add the VexNet keys to the cortex and joystick controller and power them both. Make sure you turn on the power button on both the joystick and the cortex. A Vela link is as shown. A VexNet light will be blinking a fast green on both units. The robot light will wink green, be mostly on both units, and when using fully charged batteries. Very important that your batteries are fully charged. It will take about 10 to 15 seconds for a link line to be established. The joystick's light will be solid green. So the joystick will turn solid green, the very top one, when fully charged batteries. If it fails, turn off both the cortex and the joystick and try again. Pairing instructions. Default code is automatically set once everything is paired appropriately. In order to test, you can add either the motors directly, or I would advise the motor controllers and then the motors attached to them. But add the motors and test. Plug the VexNet motors plugged into the motor port 2 and motor port 5. With default code, pushing joysticks channels 3, so this will be up, and this one up to turn clockwise. Pushing joysticks channel up 2 will cause the motor 5 to turn counterclockwise. And this is the default code. Later on, we'll show you how to change the code. Programming your robot. We'll be programming the robot with Robot C. Robot C is a C-based programming language used in education, robotics, and for competitions. Using Robot C, you will be able to instruct your robot to carry out tasks autonomously as well as respond to the control inputs. Don't worry about the autonomous response. We will not be using this in this particular competition, in this level. On this particular section, we will meet again December 16th for a question and reflection on this course. Students will question, reflect, and collect resources to design a prototype solution for the problem. Thank you. Hello, everyone, and welcome to Everyone is an Artist and Engineer. November 15 training, energy infrastructure, wind, oil, and natural gas, VEX Robotics.
Welcome to Everyone is an Artist and Engineer, 2014-2015 Energy Infrastructure, Wind, Oil, and Natural Gas, VEX Robotics Teacher Training for middle school and high school. I'm your instructor, Felipe Resendes. Under the Academic Year Pacing Guide Saturday Workshop, we are under Cycle 3, January 10, 2015, under Design Prototype for Interdisciplinary Connections. Basically, that means that you should have your students already at the point where they will design their prototype or prototypes of their CSTEM challenge and projection solution. So if you haven't already gone through the first couple of phases of the engineering process, you should be at the construction phase at this point, just to kind of give you guys a quick overview. Today's training outline, we're going to go over programming. What is programming? The top 10 programming languages currently in the market or in the industry. We're going to go over sample code in Robot C. Just a brief on the sample code, what it might look like. No real coding today. Hopefully in the next sessions coming up, we'll be able to actually go over some code and run it and compile it and show you how it actually gets loaded to the actual robot. We're going to be installing Robot C, which what requirements are needed for a new installation. The license manager, if you already pre-installed, if you have already pre-installed the software, you have it installed as a trial basis. And we're also going to go over the installation process, and at the end, a couple of hints and tips. What is Robot C, or what is programming? Programming is a process of creating a sequence of instructions that tell a computational device, and this could be a computer, or in this case, such as a microcontroller on a VEX robot, how to perform a task. The VEX ARM Cortex-based microcontrollers are pre-programmed with default code that allows you a simple way to get started without writing and downloading code. However, more complex robot configuration and behaviors are possible through programming. So again, there's default code that comes automatically with your controller that gets built into it already from the makers of VEX. There are several options for creating and downloading programs to your VEX robot, such as Robot C for VEX Robotics. Another option might be ACC as an alternative if you feel more comfortable using ECC, or something you guys might be able to use as well. Using Robot C graphical mode, you can drag and drop blocks of code from the graphical functions menu to create a program even faster. Robot C has switched to a graphical mode almost as the other GUIs like LabVIEW and etc. that are currently very popular in the market. You'll see this version as the version 4.27, if my memory serves me correct, on this particular installation later on. There are two types of code with Robot C. We have autonomous code and radio control code. Autonomous code, what the name implies, autonomy means that by itself. Autonomous code allows a robot to perform behaviors without input from the radio control transmitter. The robot follows pre-programmed routines, responding only to sensor input. So basically, this is basically the robot doing its thing. Kind of like cars nowadays, they're starting to drive by themselves. I mean, they have all these sensors that are being programmed to do specific functions. Once they hit those parameters or behaviors or limits, they'd be able to do the programming that's been added to them. And without any user interaction, because you do have eventually control of the robot, kind of like a wireless RC card towards the towards the competition. Now, radio control is the one I was talking about a second ago. The radio control code allows you to configure the way in which the radio control transmitter controls the robot, allowing a human operator to provide input to the robot. So if you select to open a claw on the X button, it will open the claw. Or if you want to do it as a up and down stick, you can do it as well. But that's you actually allowing and configuring the actual radio control transmitter. Those are the two types of robot codes, and there's a mix: autonomous code and radio control code. Some competitions like FRC allow you to do that, or I'm sorry, First Tech Challenge allow you to do that. First couple of seconds are autonomous code, and then it switches over to radio control code. Best Robotics allows you to do the same thing as well. Top 10 programming languages. Now you may ask yourself or your student, why do you want to learn programming? Where here are a top 10 and what some of the applications that are currently being used at. According to the results, here are the top 10 programming languages of all platforms: mobile, web, desktop, and embedded. Anything you use from your VCR has to be programmed. There's the firmware that gets installed. So it recognizes inputs, your mobile devices, the World Wide Web. This right here is the actual World Wide Web. Then we have mobiles right here and computers. So Java is almost on these top 3 and very popular, followed by C, which is a version of Robot C. C and C++ are pretty much brothers and sisters. They are in the same area in how you code. So on all these, you can have them on their phones, computers, and actual circuitry for different types of electronics. So as you can see, C is pretty high up there. We have Python, another very popular programming language, C, PHP for programming web servers and database servers. JavaScript, again, a version of very similar to Java, it just allows to add functionality to the actual websites and stuff like that. Ruby, which I've never worked with, and R, and I have worked with a little bit of MATLAB. So those are the top 10 programming language in the IEEE spectrum, and they come up with their own criteria on how they came up with these top 10. What you're looking at right now on your screen is a sample code in GUI interface. This is Robot C. At least in the last couple of years, this is what the code would look like when you were writing your code. Task main would automatically be put there by the actual, if you wanted to do a motor or a movement, you actually do under motors moving forward, and it would automatically input all the tasks here. So there's not a lot of coding except for what you're going to do on the parameters. // go forward at full speed. Again, when you see / here under hint, Robot C will allow you to document your code in green text by adding two /. This here, you can add as much code as you want. And we recommend you guys that when you're writing code line by line, what is happening? What are you doing? I would even code every line, like example, code line 4, motor left going 127 or full speed. You can actually code as you go along off to the side as well. And line by line, motor, run motor forward and then stop for 1 second. So while moving forward, compile on, and it was compiled. This it gives you the date that it was compiled. It was basically is when it's actually processed, so it can run the actual code. Compile, if it doesn't pass the compiling and there's errors, it will not be able to load to your robot, or it's going to have errors, and your robot's not going to do what you think it's going to do. So it's very important that there are no errors when you compile and load and send it to your VEX Next Cortex. But this is just the very basic. As you can see, a lot of your simple command windows are up here, and these are very similar to you. You've been using it for many years, and of course, this is your function library that you use to actually call up all the main servos, sound, timing, motors, etc. Hardware requirements for a new installation. While setting up VEX, you need Windows XP Service Pack 2 or later. Just strongly recommend you guys face off XP because it's no longer being supported by Microsoft. So be real careful. Go ahead and at least try to have Windows 7 as a very comparable operating system that I feel very comfortable with in the last couple of years, and even Windows 8. Hardware needed, VEX programming hardware, AA cable. That's the USB cable, the long one that has 2 identical sides, and then your orange programming cable, and an orange programming cable. 2 VEXNet USB adapters, a VEXNet Cortex, and a joystick. So you're going to need all this. Other considerations, make sure that you're actually a local computer administrator. You'll be able to install software. If you're not, I strongly recommend you go to your IT department, the person in charge of your school, and see if they can get permission to install the actual Robot C. If you already installed Robot C 4.0 manages your Robot C and Robot Virtual World licenses. It is designed to simplify the process of keeping all of your software up to date while minimizing the number of downloads and installations you must perform. Once you have downloaded any version of Robot C 4.0, you have everything you need. NXT and Cortex drivers excluded. So if you're working with NXT or you need to download the drivers. No additional downloads of Robot C software are required. In fact, don't try to download and install additional versions. So if you already have one version, don't re-download a 4.1 or a 4.2 or 4.7 if you already downloaded 4.1. And you can always get more information on the resource link mentioned down here. Installation process, go to the www.robotc.net/download/VEX and select on the Robot C version 4. So you're going to go to the downloads pull-down menu and select the VEX Robot 4. You can even, there's also, I believe, If you're more familiar with Robot C 3.x for Cortex and PIC, you can also, I would stay away out of these, but I'm sorry, for VEX, it might work, but you just want to make sure you select VEX Robotics. Click on the blue download button, version 4.2.7 when you see this, once it comes up, and save the program to your computer and run installation. I encourage you maybe to the downloads or to your actual desktop, so somewhere you can know you're going to be able to have easy access. During the installation process, you're going to see a couple of screens. The welcome screen, go ahead and just click next. This is the EULA, or the user license agreement. Make sure that you select accept the terms and license agreement. If you're like me, you know, I like to read through this stuff. I don't know why, just one of those crazy things I like doing. 99.99% of the people don't read, but I do like to read some of the stuff. I want to say more than 80% of the time. Installation process, click finish and complete installation. So once you go through it, it's gonna ask you to come up with this particular setup. Click finish. Okay, and if you already if you were issued a license from the system staff, I'm not 100% sure this is going to happen to everybody or who's requesting a license, but you can actually go to manage license. You can click add license button, which will be right here at the bottom, and then we can go ahead and add your license ID and password, so you can have the latest version for the allotted amount of time the license has been purchased for. And a couple of hints and tips, which I won't take any more of your time, is do not forget to install the USB driver. So you're having issues that it's still not connecting or not reading your computer. It's definitely the time where you can go back to the Robot C web page, which is here, and go ahead and install some of the firmware or updaters before using Robot C. Make sure if right here, recommended downloads, USB to serial drivers, etc. that you might need for this particular process. Again, thank you, and see you on the next session for February 7, 2015.